When the shelves empty and the grid goes silent, steel knowledge becomes survival capital. Every generation assumes the hardware store will always be there. Steel tools, replacement parts, propane refills, welding rods, they're just a short drive away, right? But, supply chains are complex, fragile systems. If they fracture, the average garage workshop becomes a museum of unusable scrap. Most modern tools depend on alloys, treatments and processes that simply cannot be replicated without industrial infrastructure. The common belief is that high-performance steel requires electric furnaces, precision thermocouples, and global logistics. But, history disagrees. Viking-age smiths forged blades that cut, split, and endured brutal conditions using clay furnaces, hand bellows, charcoal, and even bone. In a true collapse, that knowledge outweighs any boxed tool set. This is not a fantasy reenactment. It is metallurgy stripped to its essentials. Viking chemistry was controlled carbon management, not myth or magic. The core principle behind performance steel is carbon content. Pure iron is soft. Introduce carbon and you create steel. Increase carbon within limits and you create hardenable steel. Viking smiths understood this practically, even if they did not describe it in modern chemical language. They often began with bloomery iron, produced by smelting iron ore with charcoal in a clay shaft furnace. The resulting bloom was a spongy mass of iron and slag. Through repeated heating and hammering, slag was driven out and the iron consolidated. But iron alone was not enough for cutting edges. To improve performance, smiths introduced carbon through carburization. Carburization involved heating iron in contact with carbon-rich material, often charcoal and bone, inside a low-oxygen environment. Carbon atoms migrated into the iron's surface layers, converting it into steel capable of hardening. This was not guesswork. It was repeatable chemistry governed by temperature and time. The clay furnace is simple to build, but, surprisingly powerful in capability. A functional furnace really needs 3 elements: insulation, airflow, and fuel. When you mix clay with sand, you get a durable refractory body. You want to shape it into a vertical shaft, with an opening at the base for air intake, and of course slag removal. The internal diameter doesn't need to be large at all. Even a narrow chamber can reach the necessary temperatures if the airflow is steady. Charcoal is the ideal fuel because, it burns hotter and cleaner than raw wood. You'll want to position a tuyere, which is just a simple clay or metal pipe through which air is introduced. A hand-powered bellows attached to the tuyere provides consistent oxygen and really intensifies combustion. To apply this method today, you'd construct a small clay furnace about knee height. Make sure to allow it to dry completely before firing. That's important. Start with a gentle warming fire to prevent cracking. Once it's cured, you can increase both the fuel and the airflow. When you see a bright orange interior, that's your sign the temperature's sufficient for forging and carburization. Right, so bone is not a superstition, but a carbon delivery system. Animal bones, when properly carbonized, become bone charcoal. This material contains carbon along with calcium phosphates and trace minerals. When crushed and used in a sealed environment with iron, bone charcoal supports effective surface carburization. To prepare bone charcoal, Clean bones thoroughly to remove fat and tissue. Dry them fully. Place them in a sealed metal container with a small vent hole to allow gases to escape. Heat the container in a charcoal fire until the smoke subsides. After cooling, the bones will be black, brittle and lightweight. Crush them into coarse granules. For carburizing, pack iron pieces inside a clay-sealed box layered with charcoal and crushed bone charcoal. Seal the lid with wet clay to eliminate oxygen infiltration. Place the container into the hottest section of the furnace and maintain high heat for several hours. The longer the exposure, the deeper the carbon penetration. Forging and heat treatment. Well, they really determine whether the blade thrives or fails. After carburization, the steel must be forged and heat-treated correctly. You need to reheat the steel to forging temperature and shape it with controlled hammer blows. But, you've got to avoid excessive reheating because that can burn carbon out of the surface. Once the blade shape is complete, normalize it by heating it to the critical temperature and allowing it to air cool. That step refines the grain structure. Then reheat again to the critical temperature, which you'll know when the steel becomes non-magnetic, and quench in oil. Oil, by the way, reduces the risk of cracking compared to water. The hardened blade will be brittle, and that's where tempering comes in. So you reheat gently until the polished steel shows a light straw colour, then allow it to cool. This balances hardness with toughness, making a functional survival tool instead of, a fragile ornament. A practical test is simple enough. Just attempt to file the edge lightly. A hardened edge resists the file. Then try to cut a rope or shave wood. At the end of the day, real-world cutting performance matters more than theoretical hardness numbers. Pattern welding shows how the Vikings maximised the material they had. Viking smiths often combined layers of differing carbon content steels through forge welding. This technique improved resilience and edge retention by blending hard and softer layers. While not strictly necessary for survival blades, it really demonstrates adaptability. In a modern application, if you have access to mixed scrap steel, you can stack and forge weld layers to combine properties. Make sure to clean surfaces thoroughly, heat to welding temperature, apply flux like fine sand or ash, and hammer firmly to bond the layers. This process takes a bit of skill, but it reflects the Viking approach. Use what you have and refine it through fire and force. Knowledge is the only tool that does not rust. In a doomsday scenario, hardware store tools eventually dull, break, or wear out. Replacement becomes impossible without supply chains. But if you understand bloomery smelting, carburization, forging, and heat treatment, you can rebuild your cutting tools from raw materials. Start small. Practice carburizing mild steel rods before attempting full blades. Observe how case depth changes with time. Experiment with quench mediums. Record your results. This is how historic smiths learned repetition, adjustment, refinement. The myth that modern metallurgy is the only path to performance steel collapses under the weight of history. Clay, bellows, charcoal and bone built empires and carved trade routes long before industrial grids existed. If this exploration of Viking chemistry and grid-independent steel-making sharpened your understanding of real survival capability, subscribe to the channel and share this episode with fellow history enthusiasts and preparedness-minded viewers. The future belongs to those who remember how the past worked.